Okay, let's get started. My name is Vince Mazer, and I'm a product marketing engineer here at Altium. And today we're going to discuss impedance calculation for transmission lines in Altium Designer 20. So let's go ahead and review our agenda. But before I do that, I want to mention that throughout our session today, we're going to initiate several poll questions. This helps us understand better how our customers are designing and what challenges they're encountering. We also are going to be taking questions in the Q&A panel, and after we're through with the prepared remarks and commentary and demonstration, we will open it up to address those questions if they are not answered in the chat window. So with that, let's talk about what we're going to review today. We're going to talk about current electronics development trends. We're going to introduce a simple concept of the transmission line model. We're going to discuss the impedance of transmission line, how transmission lines are either intentionally or inadvertently manifest on printed circuit boards. We're going to follow that with a discussion, a very important topic called return current. And then we're going to review the PCB design, some of the key PCB design rules and how they influence impedance. And then after that, I'm going to just go through the step-by-step in presentation form of how you use Altium Designer to do impedance-controlled routing and to cope with that design challenge. So let's go ahead and talk about development trends. I mean, at this point, I guess this slide is a little trite. Any of us that have been in the industry for a while knows that everything's going faster every year, and we're expected to do it in a quicker amount of time, smaller footprint, lower power consumption, etc. We've got two examples here. On the left, we've got Ethernet data rates that have been increasing dramatically all the way up to 100 gigabit and beyond these days. On the right, we have I/O bandwidth, specifically PCI, PCIX bandwidth and how that's increasing. And we're seeing that I/O bandwidth is doubling every 3 years. So as these clock rates increase, we have reduced edges of the signal, quicker rise and fall times, certainly increased data rates, increased clock frequency, all demanding increased performance. Let's go ahead now and talk about a transmission line model. This is a schematic representation of a typical transmission line. A transmission line, it's really a direct return system. The conductors are generally placed together to form a single electromagnetic field. I mean, examples of transmission lines are the cable you use for satellite or terrestrial-based cable TV, the veteran 300 ohm twin lead that's been used for television in the past and some radio reception, and a variety of different transmission lines. So anytime you have a conductor, you're going to have some resistance in that conductor. Also, because it's metal, you're going to have some inductance in there. And if we look at this schematic drawing here representing the spacing between the signal line and the return path or return line, we're going to have some separation there that's going to also create capacitance, and that's determined by the line and the materials. And then finally we've got this G, which is conductance. That's sort of the leakage, the wasted energy, if you will, that results due to the particular characteristics of the dielectric material. And these are the main factors that influence transmission line performance in general here. And we'll be breaking that down more specifically as we talk about transmission line impedance in a circuit board. We see we've got a microstrip set up here with the conductor on the top separated by dielectric and a return plane on the bottom. And what we basically have is, as the schematic says, basically the inductance, the capacitance, and such as that goes down the path. Now again, at lower clock rates, this isn't a big deal, and we'll talk about that a little later, and perhaps dive down a little deeper to discuss why that's the point. But one of the fundamentals about impedance, especially when we're talking about sending a signal down a path and then waiting for the return, is the signal source impedance should equal the receiver's impedance. I mean, that's the so-called standing wave ratio, and ideally you want all of that signal that you're transmitting down that line to be received. Now, when you have an impedance mismatch, what happens are you get reflections, and that's what we're really seeing manifest here in these two oscilloscope images. We have the signal as we really expect it down at the receiver on the left, and we have the signal as we actually encounter it there on the right, and you can see some of the original signal in that image on the right, but there's a lot of reflections and such that occur because of the mismatch of impedance, and because the impedance or the impedance that signal sees is not to the specification of the transmission and receiver. Again, just in general, your impedance equals this equation we have here, square root of L over C. One thing we want to look at here, you can see real quick that if your capacitance is going up, that value is going to get smaller, your impedance is going to get smaller. The ideal PCB transfer line impedance is between 40 and 120 ohms, certainly 50 ohms, a big one. The thing to remember is because we are using a consistent cross-section, or so-called homogeneous transmission line, that the good news is with that this important ratio is constant throughout the line, and we only need to be worried about the impedance and not the length of the line. Here's an example of routing guidelines. I mean, I remember when I used to look at routing guidelines, a lot of times it was just maybe some certainly the footprint layout, maybe some exit strategies. Well, now in this day and age, we all have to worry about differential impedance, single-ended impedance, spacing between differential pairs and high-speed periodic signals. And what we have on the left here is original USB, 480 megabit, and we have the current version, I believe that's the current version, USB 3 at 5 gigabits, and we see that there are differences. And these are part of the design guidelines now to take into account these types of parameters so that we can design our circuits, implement those circuits, I guess I should say, on the printed circuit board properly. Let's talk a little bit more of the types of transmission lines we see on today's printed circuit boards. Coplanar is when the signal and the return path is on the same layer. You have a dielectric underneath, and because of the circular nature of magnetic fields, in this case, the magnetic field is influenced by that dielectric and also the dielectric constant of air. We have a similar situation with microstrip line. That's where the conductor is on the outside layer and the return path is a ground plane. You can actually submerge that microstrip equally embedded into that dielectric and get improved performance, and that's the so-called embedded microstrip line. We see that on the third image from the top. Symmetrical strip line is where you have the conductor perfectly centered in that dielectric and surrounded by two ground planes. This is an excellent transmission line, albeit they're hard to fabricate because you really want that to be equal. Asymmetrical strip line is, as we see in the figure, one side of the dielectric is larger than the other one. So again, I mentioned it earlier, but again, it's an important concept. We want to use these homogeneous transmission lines where the cross-section is identical across the length. That's what really allows us to get all of this in balance. Now, we mentioned here a balanced transmission line is where you have a straight and a return conductor with the same length. They have the same shape and cross-section. An example of that is a differential pair. And of course, we run into both of these implemented on PCBs. So let's talk about return current. We have two setups here in the top. We've got in the upper left, you're seeing the return current representation at 1 kilohertz. Now, that return signal, it wants to find the path of least impedance. Okay, so in the case of 1 kilohertz, because the wavelengths are so long and such, and the aspect that we call capacitive reactance is totally different, it wants to take the path of a straight line. Whereas when we go higher in frequency on the upper right, we've got a 10 megahertz signal. It's hugging closer to that signal path. And again, that's that capacitive reactance, which is one of the components of impedance. And basically, it's that factor that's 1 over 2 pi times the frequency times the capacitance. So when we look at that simple equation, we can see right away that as that frequency increases, that the capacitive component, which dominates in these types of designs in most cases, is going to result in a lower impedance. And that's why as the frequency goes higher, we're going to see that return signal, which is really an electromagnetic field, hug very, very close to that conductor. Now, we've got a situation in the bottom half here, the two diagrams in the lighter shade of green, where we're showing the difference between a homogeneous transmission line. That's, again, where the cross-section is identical. And then we have a heterogeneous transmission line. We've got a slot or an area of the plane, not through the whole layer stack, but just one plane, the return plane in this case, which it has an opening, no copper. We see on the left side that the return current, flows as we would expect, close to the conductor. But on the right side, when that slot is put there, it has to go around and take a circuitous route in order to get back to that source. And this creates all kinds of issues. For instance, that return route might go over some other signal conductors, and that generates crosstalk. You get all types of reflections in here, and that generates issues trying to get your product or board to pass EMI testing. So you really want to avoid any types of slots or any other discontinuities in the return path. That's a simple mistake I know I've made in the past, which really caused some odd behavior. So let's talk about typical design rules and how they influence the impedance. Okay, conductor, we've got 4 of them across the top here. Conductor width, thickness of the dielectric, dielectric constant, and the thickness of the copper. Well, as the conductor width increases, that's going to generally decrease impedance. And there's a high correlation between that. Conductor width is a major factor in determining an impedance controlled line. There's also a high dependency with the thickness of the dielectric. The dielectric constant influences it, to be sure, but its impact is not as great as some of the other areas. And then there's a lower dependency on the thickness of the copper, again representing the aspect that there's just, there is inductance in that transmission line, but it's generally not as big of the factor as capacitance. And here are some useful rules of thumb that the industry has used for years. With a microstrip, again, that conductor being on the outside, having a return path of a plane underneath of it separated by dielectric, if the width of that trace is 2 times the height of the dielectric, for FR4, you can be basically assured that you've got a nice 50 ohm line there. Similarly, if you're using a symmetric strip line approach, the height of the dielectric would need to be 2 times the width of the conductor, and for FR4 with a dielectric constant of 4 to 4.6, that would give you 50 ohms. Okay, so now we've talked about the background, the theory, if you will, on transmission lines. Now we're going to talk about how we actually address this in Altium Designer. The first thing you need to do, in the hub for all of this, if you will, is a layer stack manager. So you open that up, you define your layer stacks, and we'll go through all of this in a demonstration. Very important to have the properties panel open. It's used a lot in these panels. And then you click on this tab down below for impedance. And what you're able to do is you're able to add an impedance profile. And you can think of an impedance profile as sort of a definition for a particular type of transmission line. Like if you go back to that USB spec we saw, there were some 95 ohm differential lines that were defined there, and you would indeed create one of those. You add that, and in this instance, we have created a single-ended being a signal that is just a signal with the return path, not a differential signal like a differential pair. And we can see that we've added that profile, and we even get in the upper left of the highlighted portion of the window, we see that we get S50. That's the default name, single-ended signal, 50 ohms. Okay, here's a bigger view of what the impedances look like. There can be many of them in the project, and we'll see how we deal with all of those. So you create your impedance profiles, you highlight the various layers, and you can change parameters in the layer in the properties panel, and you can refine this to get your impedances in alignment with your layer stack, and then be able to just get ready and apply that to the project. But before we do that, we want to talk about the types of transmission lines that we currently support in Altium Designer. So again, single-ended structures are shown on the left side here. And the conductor is obviously the smaller of the geometric shapes in the cross section, and the other one is the return path. In the case of single planes, double planes, you see we even take into account the solder mask, because indeed solder mask has some dielectric properties and aspect that can influence signal propagation. On the right side, we have coplanar single-ended structures. Again, where the return path is on the same layer as the signal, and grounds sandwiching or surrounding, I guess we should say, these coplanar structures respectively. Similarly, we have differential structures, same concept. These are all coplanar signals, right? Differential, but this again shows the cross sections that we currently support. And then finally, coplanar differential structures, where you have differential pairs and you have the return path on that same layer, again with ground on either side. So back to impedance calculation, and we'll go through this in the demonstration. But when you highlight your plane, you immediately see, when you highlight your layer in your impedance profile, you immediately see the constituent layers that make up that stack. So in this case, we see that we've got dielectric 1, dielectric 2, and the internal ground and power and top that are related to this impedance on this layer. And you see the cross section of that. The system will automatically give you a cross section of that. You see the impedance calculation. When you set up an impedance, you're able to define the impedance value, also the target tolerance. That certainly gives you more wiggle room to have trace widths and a topology that's going to work best for your design. And then here we see the resultant transmission line parameters. If we want, we can allow the system to just generate the trace width it recommends for the given parameters, or we can say, we want our trace width to be, 0.1 and hit this f sub x function button, and it will calculate everything and keep that consistent. And again, a lot of this will come through in a more clear manner once we get into the demonstration. Now, once you have your impedance profiles done, you can go into your rules, and you're going to have the use impedance profile is going to be active, and you'll be able to checkbox that and assign that impedance profile to your net and go about your design. So this is how we bring that information in. Now, what's really nice about this is if you have a lot of this done ahead of time, and you've got all these rules, these constraints, if you will, that are associated with these various nets, and for some reason you decide you need to change that impedance program, you change it, or profile, you change it once in the layer stack manager, and it echoes to all of those rules that reference that. And that's incredibly powerful over existing approaches where external calculators are used and individually annotated. So at this point, we want to go into the demonstration. So what I have here is I have Altium Designer up. I have one of our demo boards, and we're just going to go into this. So the first thing we want to do is bring up our layer stack manager. And you notice I have my properties panel already enabled. There's a lot of interaction there. It's a very important part of the interface here. So I've got this set up for 4-layer, but I really want to make it something a little more complex. So I can come in here and look at our presets. And again, what I'm doing right now is I'm setting up our layer stack. We're not doing anything with an impedance right now, but I want to go ahead and have a 6-layer design. A little more latitude there gives me the ability to show some of these capabilities. And what I'm going to do, and these are default stacks that are set up with common materials, and of course you can use your own materials as you see fit. So I'll go ahead and choose this impedance tab here, and then the system's going to bring up that environment. And just as I showed in the slides, I'll go ahead and add an impedance profile. And what I think I'm going to do is will be a little different here. Let's go 55 ohms, and let's say an 8% tolerance. And then the system's going to take all of this into account. Now, if I highlight this layer, this is going to show me my cross section. Again, we're using a nice homogeneous transmission line, identical cross section, and this is what we're getting. We're seeing that we've got our impedance is 54.992 ohms, well within our tolerance. We've got the ability to, for instance, we see that in this case, we are taking into account our solder mask. We're taking into account the thickness, the dielectric constant. Indeed, we could come here if we wanted to and just delete that layer from the stack, and the system is going to update. And we see that there is a minor change to the results. And the point is that you have a lot of granularity here to come up with what you really need to achieve your design objectives. We're using a common lead tin surface. We certainly can use any type of materials. You can go into your stack up and change that. But we might also want to take into account our surface finish. And so when I do that, again, it changes it ever so slightly. But, we're well within that tolerance. And again, the point I'm trying to make here is there's a lot of versatility. If for some reason I want this to be, just 2 millimeters, can come in here and it will do that calculation. And in that case, since I entered in my W2 as shown here in the cross section, we do take into account the etch factor. And this is if you're familiar with etch factor in the calculation, this is just merely the inverse of that common equation. We represent it because it's just in a easier to display type of format. So again, surface finish, etch factor, any types of layers. If you want, you can come in here. This is a really important aspect. You can assign a different dielectric constant, and it will take that into account. And we see that this is the cross section. We see the number of dielectrics that we have here. And indeed, we could come in here and just add one below, add another prepreg layer. And we'll see that our cross-section is updated and we have a new impedance calculation. You can also change your top and bottom references for the calculation and whatnot. Now for internal, we see here's a good example of where we have one of those asymmetrical strip lines. The dielectric on the top is a little less, or is less than the dielectric on the bottom. Now, my understanding is that there are times when you get this material at your PCB fab. It comes on rolls, and if for some reason the rolling order is different, you can actually invert the stack up, so it will take that into an account, and that's what this trace inverted indicates here. Library compliance just says, hey, I think we may have an example here. I think I manually changed one of these layers to 4.7. If I go library compliance, I'm going to get a flag here that it says, hey, it doesn't match your library material. So this gives you the best of both worlds where you can really play around. And if you decide that you need a different type of a stack up, you can determine those numbers, but you're also flagged if you do have something that's in disagreement with your library. Go ahead and turn that off for now. Now let me go ahead and also mention that we have roughness factors you can take into account. You've got different models you can use. These are just different mathematical approaches to solving for impedance given these various factors. You can take into account surface roughness in micrometers. There's a roughness factor. What we're trying to provide are all the knobs, if you will, to allow you to tune the performance of your design to what it needs to be. Now what I'm going to go ahead and do is I'm going to go ahead and enter in another impedance profile. This one we're going to make differential. And I think I'm going to go like, I don't know, maybe 95 ohms on this one. So again, we can look at the outside. This shows our cross section. Here's our bottom one. And I've set this for 10%. We've got the calculation where we want it. We've got our trace gap defined to 0.127. Well within tolerance. I mean, this is 0.006% deviation. I might also mention that on the display here, you can widen this and you see all this great information right here on each layer. So it shows you what the width is, what the trace gap is, what your impedance is, the deviation, and even the delay in this case. And we can also see this here, delay in nanoseconds per meter. So this updates just like a spreadsheet every time you make a change. So for the sake of our demonstration, I'm going to say, hey, that looks great. I'm going to go ahead and save my layer stack. Okay, and now I'm going to go back into the printed circuit board, and I've got a differential pair here. And what I'm going to do is go into design rules. And you see here now I've got this, and we actually see the top in the list. Now it doesn't put the single-ended impedance profile in because it's a differential pair. So Altium, takes away the guessing by only putting the relevant impedance profiles in the selection list. And we see when I select that, it fills the display here with that with the trace widths. You remember we saw we had a 0.127 millimeter gap. And what I'll go ahead and do is apply this. Now this guy, if I come in here to measure primitives, I think we'll see that this gap is different on this trace right now. Yeah, it's 0.32 millimeters. So what I can do is, that begs the question when you have a situation like this and you've made a change, let me go ahead and just highlight this, and then I can come in here to the routing menu and do retrace. And what it's done is it's applied that impedance profile and automatically updated the trace. And if we want to see that, we can come in here and do the measuring of the primitives again. And we should see 0.127 millimeters, which is 5 mils. And so this really is incredible in allowing you to update your designs as you refine impedance. Now, if I went back into this stack up and added a different impedance parameter or change the one that I'm using right now in this differential pair, I would change it once and I could apply it to many without the risk of having errors. And that's what I wanted to cover today. So with that, I would like to again thank you for attending today's webinar and wish you to have a great day. And we look forward to your attendance on future Altium events. Have a super day. Take care now. Bye-bye.